When we look up on a clear night, the star field seems like a window without end. It's easy to imagine space as a limitless expanse where galaxies go on forever, but we are actually looking at a restricted view. Our perspective is governed by the finite speed of light, which acts as a physical barrier to what we can perceive. This creates a sphere around Earth known as the observable universe. Its edge represents the maximum distance light has managed to travel toward us since the beginning of time. We are watching a delayed projection of the past, sealed inside a cosmic bubble that prevents us from seeing anything that happened outside its walls. This bubble presents a strange mathematical problem. The universe is 13.8 billion years old, yet the edge of our vision sits much further away, about 46.5 billion light-years in every direction. That discrepancy exists because the universe is expanding. While ancient light was traveling toward us, space itself stretched the gap between Earth and those stars, moving them far beyond where they started. Because of dark energy, this expansion accelerates. The void is growing faster and faster, actively pushing the universe's edges away. We are caught inside a bubble where the very fabric of space is pulling the rest of the cosmos out of our reach. To map this cage, we have to look at the particle horizon. This is the absolute limit of light launched in the past that has had enough time to reach an observer on Earth today. But there is a more permanent boundary called the Hubble horizon. This marks the point in space where the expansion is so rapid that objects are moving away from us at the speed of light. If a star beyond this line emits a signal today, it will never reach us. Even though light is the fastest thing in the universe, it cannot overcome a gap that is growing even faster than light can travel. These horizons effectively quarantine the most distant parts of the universe, ensuring that those regions remain permanently invisible to us. Even well within these observable limits, the universe is far from uniform. Large sections of space appear strikingly barren, containing vast regions known as cosmic voids. The Bootes void is one of the most extreme. It spans roughly 330 million light-years across, a distance that should contain thousands of galaxies, yet astronomers have only ever spotted a few dozen. These immense stretches of nearly empty space force us to question our current understanding of gravity and how the cosmic web organized itself billions of years ago. If the horizons of light set such a strict limit on our vision, we have to find other ways to look into the invisible parts of our universe. One method involves hunting for neutrinos. These subatomic particles travel at nearly the speed of light, passing through matter and light-trapping barriers without stopping. We can also listen for gravitational waves, tremors in the fabric of space-time created by violent collisions of massive objects. These ripples carry data across the universe, even when there is no light to be seen. By utilizing these alternative physical messengers, we are finding ways to sense the cosmic landscape that traditional light can no longer reveal. However, the window for these observations is closing. Billions of years into the future, the accelerating expansion of space will bring a fatal isolation. Eventually, the event and Hubble horizons will collapse inward. They will shrink until they enclose only our local group of galaxies, permanently cutting off the path for light from any other part of the cosmos. Inside this isolated pocket, the stars will eventually die out. They will fade into white dwarfs and then black dwarfs, leaving the sky without a single point of light. Any observer born in that era would look up into a total void, with no physical evidence that the rest of the universe ever existed. This bleak future highlights just how privileged our current position really is. We are alive in a specific window where the universe is still largely visible. Because we exist now, we can still detect the residual heat of the Big Bang, the cosmic microwave background radiation that fills the sky in every direction. This is the very signal that Arno Pausius and Robert Wilson first recorded with this radio telescope. It was a breakthrough that confirmed the origin of our universe, captured before the expansion of space stretches it into undetectable frequencies. Our horizons aren't just boundaries, they are a ticking clock. Every year, more of the distant universe slips away, and we are challenged to map the cosmos and understand its origin before the signals fade into the dark for good.